Welcome to Maths with AJD. In this video, we are still talking about systems of differential equations, and here I'll be talking about phase plane analysis for systems of differential equations. Okay, first of all, let's see what this is about. Phase plane, phase plane analysis is a powerful technique used to analyze the qualitative behavior of nonlinear dynamical systems. It involves plotting the trajectories of a system of differential equations. In a coordinate system, defined by the system's variables, defined by the system's variables. Often called the phase plane. Each point in the plane represents a state of the system and the trajectories describe how the state evolves over time. Okay, now let's talk about critical points and stability. Critical points and stability. Critical points, which are also known as equilibrium points, or fixed points, occur when the system reaches a state where the derivatives of the variables are zero. In other words, the system is in a steady state. The system is in a steady state where there is no change. There's no change in the variables over time. Okay. For a system of differential equations, the t equals f of x comma y, and dy dt equals g of x comma y. Okay, so we can have this f now, this one now we can so the equilibrium point is actually where you have f of fxc yc, that's critical value of c and critical value of y, and that is 0. On the other hand, we have this gxc comma yc, so the critical value of g is equal to 0 also. In that case, we can then have we can have j of x comma y in that case to be equal to partial f, partial x, partial f, partial y. Then here we have partial g, partial x, and partial g, partial y, which is called the Jacobian matrix. So this is called the Jacobian matrix. So this can help us to get the stability of the system when we find its determinant. We've done that this a couple of times, but this is the first time this is like an official introduction to the concept. So let's talk about classification of equilibrium points. I guess I want to switch pens here. So classification of equilibrium points is really useful. When we solve the Jacobian for the eigenvalues, it helps to find, to know the type, what the kind of equilibrium point is. So classification of equilibrium points. So equilibrium points can be classified based on the eigenvalues, of the Jacobian matrix, which we just got up there, the eigenvalues of the Jacobian matrix. And these are the possibilities we have. The first possibility is a node. You can have a node, and in a node, right, both eigenvalues are real and have the same sign, either either both positive, either both positive or both negative. Okay, and here the trajectories are straight lines. They are straight lines, either either approaching or diverging from the critical point. So this can come in two forms. We can have a stable node. We can have a stable node. Of course, we know the two signs are the same, but for a stable node, right, both eigenvalues, both eigenvalues are negative, and that means stability. Both eigenvalues are negative, and trajectories approach the critical point. Trajectories approach the critical point. A very good example will be when you have, say, lambda 1 is -2 and lambda 2 is -5. Okay, so because these two eigenvalues have negative sign now, then you can say that you have a stable node. Okay. Then um we can have an unstable node. Obviously, that is when both signs are the same. Both signs are positive actually. Unstable node now. So that talks about divergence. So both eigenvalues are positive. Okay. Both eigenvalues are positive and trajectories diverge diverge away from the critical point. Okay. So, I mean, if you want to represent this up here, right, it's more like you have let's say this is the critical point. Okay, let me plot a graph. So imagine you have a critical point here. So for stability now, you have all the trajectories are coming into this same space. Anywhere they are coming from, they are entering that place, you know. But in this other case now, when you have maybe, okay, let's give an example. Imagine you have an example. Instead of -2, -5, you have lambda 1 is 2 and lambda 2 is 5. Okay, a very good example of that would be when you have, say, you have this, and this is like the critical point. So because those things are positive now, so you have trajectories diverging away. So anything that comes just moves away from the critical point. So there's a moving away from the critical point. So that means there's no stability. And that is why, if you look at it in mathematical terms, you have something approaching infinity. But in this other case, it's going to zero, kind of. So because everything is moving into that system. Okay. So that's when we talk about node. Now let's talk about another one, another type of another class of equilibrium points we can have will be what we call a saddle. Saddle. So in this case, one eigenvalue, one eigenvalue is positive, okay, and the other is negative, okay. So there's a kind of confusion, right? So the trajectories, the trajectories approach the critical point along the stable direction, along the stable direction, and that is associated with the negative eigenvalue. So the negative eigenvalue gives it the trajectory approaching the critical point associated with the negative eigenvalue. But of course, we also have a positive eigenvalue. So we have a divergence in that case. So and away diverge away from the unstable direction, from the unstable direction. So and that is associated with the positive eigenvalue. Okay. So an example of this would be when you have lambda 1, maybe lambda 1 is -2, whereas lambda 2 is equal to 5. Okay. So in that case now, imagine that you have this. This is the critical point now. So let's say everything coming from this direction. Okay. What do I do now? So let's say, okay, let me do some kind of so let's say everything, so we have two sides. I'm just doing something hypothetical, right? So you have two sides. Everything coming from this direction now is for lambda 1 equals -2. Okay. So here now, everything coming from this side goes towards this, goes into the critical point. Everything coming from above, so to speak. But everything coming from under goes away. Okay. Everything coming from under the line diverges away. So that is what you now call a saddle, because you have some are entering, some are getting out. So that is a good example of a saddle point. of a saddle rather. Okay. Then number three, we have what we call a spiral. Number three, that's another class of equilibrium point. It can actually be a spiral. Okay. It can be a spiral. And the idea of a spiral is that the eigenvalues, the eigenvalues are complex. They are complex with a non-zero real part. Non-zero real part. They are complex with a non-zero real part. Just like you know, a complex number has both real and imaginary parts. So they are complex to non-zero real part. Okay. So if the real part, if the real part is negative, okay, the trajectories, the trajectories, the trajectories spiral towards the critical point. The trajectory spiral towards the critical point. Okay. And that is called the stable spiral. That's called the stable spiral. Okay. And and if the real part, if the real part is positive, okay, the spiral, the spiral away from the critical point. The spiral away from the critical point. Okay. And that is called the unstable spiral. Unstable spiral. Okay. So let's take examples of each of these types of spirals, for instance. Let's take a stable spiral. So for okay, talking about examples now. Examples. So imagine we have a stable spiral, stable spiral. So for a stable spiral, we say if the trajectory is, if the real part is negative, okay? If the real part is negative, so that means we have something like lambda 1 equals minus 2 plus I. Then lambda 2 is something like minus 5 plus 2i, whatever. So let's imagine that's what we have. So in this case now, imagine that this is the critical point. So because we have complex parts, then we are talking about spirals there. And because both the real parts are negative, so we're going to have the spiral moving into, so it's more like you have something moving into, how do I do this now? So it more means you have something coming from outside and then it's moving into the critical point. So it's moving into, that's what we mean by a stable spiral. So it's spiraling because of the complex parts, but then because of the negative real parts, then it's spiraling into the critical point. That's an example of a stable spiral. On the other hand, we can have an unstable spiral. So what that is about is that maybe now lambda 1 is equal to 2 plus the same I, and lambda 2 is 5 plus 2i or whatever, as far as it is complex. And now you have this, and this is the critical point. So, and because these real parts are positive, so we are going to have an unstable spiral. So in this case now, you have the trajectory growing out of moving away from the critical point. So from here now, you have the trajectory moving out, growing out of the critical point. So you have this going out of the critical point like that. So that is what we mean by an unstable spiral, because it's going out of that. So that is about a spiral. Now we have a fourth type of equilibrium point, which you call a center. Okay. We have that as a center. So for a center, right, the eigenvalues are purely imaginary. The eigenvalues are purely imaginary. Okay. That means that the real part is zero. The real part is 0. Okay. And leading, uh, leading to closed orbits. So leading to closed orbits around the equilibrium point, around the equilibrium point. Okay. Around the equilibrium point. So the system exhibits, the system exhibits periodic motion around the critical point, around the critical point. Okay. It's almost about the movement of the solar system around the sun, right? Something like that. So the system exhibits periodic motion around the critical point and trajectories, trajectories neither converge, neither converge nor diverge. Okay. So centers are typically seen, they are typically seen in conservative systems that don't change, so to speak, in conservative systems. So if you're going to take an example, it would be something like this. Here you have, say, lambda 1 now is just, maybe lambda 1 is plus I, and lambda 2 is plus, lambda 1 is I, or basically we can have lambda 1, lambda 2 together as plus. Okay, let me just do what I've been doing. So lambda 1 is I in short, and lambda 2 is equal to 2I. So basically complex. In that case, imagine if this is the critical point, then what you have is a center. So we have oscillations, right? So we just have a center. So it's just moving in no particular direction. And that is how a center looks like. So those are the four possibilities when we are classifying equilibrium points. Okay. So it can be a saddle. It can be a node, it can be a saddle, it can be a spiral, and it can be a center. Okay. Now let's Um, okay, let's talk about face portraits and qualitative behavior now. Face portraits and qualitative behavior. Okay, face portraits and qualitative behavior. Qualitative behavior of nonlinear systems. Okay, so a face portrait is a visual representation, the visual representation of the trajectories in the face plane. Okay. It provides it provides it provides insight into the behavior of the system as a whole, and is especially useful for nonlinear systems for nonlinear systems. Okay. The portrait maps out it maps out it maps out the critical points the critical points along with the trajectories, along with the trajectories that lead towards or away from these points. Okay. And just like we've seen before, we can talk about stable nodes. So stable nodes, that's where we have only real parts with the same sign. So stable nodes, meaning they have both just negative values, right? So stable nodes will have trajectories, trajectories that converge, just like I showed before, that converge towards the equilibrium, towards the equilibrium from all directions, from all directions. That is a stable node. So I think I showed that previously. This is a very good example of a stable node. So from all directions, everything goes into the critical point. Okay, that's a stable node. All right. So, and then we move on to the next one where we have unstable nodes. Okay, I wanted to change this. Unstable nodes, unstable nodes will unstable nodes will have trajectories that diverge away, from the equilibrium in all directions, of course. So unstable nodes, all the trajectories will diverge away from the equilibrium. This is a very good example. Oh, yeah, that is a saddle, sorry. This is a, yeah, so from the equilibrium, everything goes away. All right. So this is not the one I was talking about. So everything goes away from that. Then next, we have saddles, just like we said before. You have saddles. Saddles will show trajectories that approach approach along one direction. They approach along one direction and diverge along another and diverge along another, often forming often forming hyperbolic patterns, often forming hyperbolic patterns. That's a saddle. So in the direction, there's an approaching of the center of the saddle of the critical point. So see this. So you see everything coming in this direction is going inside, whereas everything coming from this direction is going outside. That is, so that's why this is a saddle point. Okay. Then we have spirals. We have spirals, yeah. So the next thing will be about spirals. So spirals display display trajectories, okay, that uh, that either spiral towards or away or away from the equilibrium point, from the equilibrium point. So we saw spirals before now. So um so this is a stable spiral which goes towards the equilibrium point, and this is an unstable spiral which goes away from the equilibrium point, just like we have there. So that's an unstable spiral. And lastly, we have centers. Centers just form an orbit, okay? So centers show closed circular, closed circular or elliptical paths around the equilibrium, indicating oscillatory motion, indicating oscillatory motion. Okay. So, and we saw that also, this is simply a center. So you just have movement around the equilibrium point, around the critical point. Okay. Then, so with that done, can we take an example? Let's take an example to drive home the points. So, okay, let's take this. So, example. So, consider the system. Consider the system dx dt equals x minus y squared, and then dy dt equals y plus dy dt equals y plus x squared. Okay, so the first thing we want to do is to find the equilibrium point. Okay, to find the critical points, set the right hand side of both equations to 0. Okay, so that means we have this right hand side, x minus y squared, y plus x squared. We set them to 0. So we have x minus y squared, all right, equals 0. And we have y plus x squared equals 0. Okay, and we solve simultaneously. Now, what can we do here? So from this place, so from here, right, we know that x is equal to y squared. Okay, that is what this translates to, that x is equal to y squared. And with this now, we can come over here and say that since x is equal to y squared, so this means that we have y plus y squared again equals 0. Okay, so from here we move here. Okay, so wherever you see x, you put y squared. So that means that y plus y raised to power 4 is equal to 0. And if that is the case, so it means that we have y into y cube plus 1, or y into 1 plus y cube equals 0. Okay. And that simply means that we have y to be equal to 0, or, I mean, we also have y cubed plus 1 equals 0, which we can deal with later. Okay. So, I mean, here, y cube, we can even deal with it right now. Y cube is equal to minus 1. So, y alone is cube root of minus 1. And the cube root of minus 1 is simply minus 1. So, we have two values now. So, we have y is equal to 0 and y is also equal to minus 1. Okay, y is 0 and y is minus 1. So, minus 1 times minus 1 is minus 1, right? So, we have these two values now. Okay, so we can use that to get our x back. Okay. So putting y equals 0 and y equals minus 1 into where we're coming from, right? This expression that x is equal to y squared. Okay. So we know x is equal to y squared. So that implies that so when you say y equals 0 now, so we simply have we have x to be equal to 0 squared, and that is equal to 0. So in that case, we have 0, 0. So that means x comma y is equal to 0, 0. In fact, I mean, this is what we call yc and xc and yc in particular, because now it has been equated to 0, right? So we have xc and yc here is equal to 0, 0. So this is one critical point. So this is one critical point. Okay, we can find another critical point here where we say that, of course, from x equals y squared, when we take y to be minus 1, which we got there, all right, so we can have x to be equal to minus 1 squared, which is equal to 1. You know, minus 1 squared is 1. So we have another xc, yc, okay, equals, when x is 1, y is minus 1, something like this. So this is another critical point. So we have got two critical points here. So we have two critical points. So the next thing we want to do is, okay, I mean, I can even say, so we have two critical points. We have two critical points. Okay, that is 0, 0, and 1, -1. Those are the two critical points. So the next step we need to take is the next step would be to linearize the system. So linearizing the system. In clear terms, don't forget what we started out with. We started with the fact that the x dt, okay, the x dt is equal to x minus y squared. And here we can call this one f if you like. Then we have dy dt, okay, equals y plus x squared. And this is equal to g if you like. So, and now we need to find, in linearizing the system, it is the Jacobian that we need. So we need the Jacobian, and don't forget the Jacobian is j of x comma y, and that will be equal to df dx, df dy, like this. Then then dg dx, and dg dy, yeah. So we have this. And what that simply means is we differentiate those things we have labeled, right? So this f now differentiates it with respect to x, and there you get 1. Then the same f differentiates with respect to y, and then you get minus 2y on this side of things. Then when you come here, this is your g. Differentiate your g with respect to x, you get 2x here, and then differentiate that g with respect to y, and you get 1 in this corner. So this is what we mean by linearization, okay? So you have this. So the next thing you want to do is you evaluate each critical point, okay? So evaluate the Jacobian matrix, J of xy, okay, for each critical point, So imagine you take the first one. So at 0, 0, we have j of 0, 0 to be equal to, you know what we had before? That's so this is 1 minus 2 times 0, that's 0. Then 2 times 0 is also 0. Then 1 here. Don't forget, we have 1 here. Y is 0, so 2 times 0 is 0. 2 times 0 for 2x is also 0. So you have this. And from this now, what do we do? Um, so we need to find we need to find the uh the lambdas. Okay, so we say to find the eigenvalues, right? We found out a couple of times. So I'll just go straight. To find the eigenvalues, we just have this 1 minus lambda, 0, 0, 1 minus lambda. The determinant of this will just be equal to 0. And in that case, we just have minus lambda into minus 1 minus lambda into 1 minus lambda. This minus 0 times 0, and all of this is equal to 0. So in short, we have 1 minus lambda into 1 minus lambda equals 0. So here we have lambda 1 is equal to 1, and lambda 2 is also equal to 1. So, I mean, in clear terms now, we know that, so we can say, so at 0, 0, trajectories move away. They move away. They move away along both axes. Because we have both numbers are real and positive. They move away along both axes. So we have an unstable node from our classification before. So both positive means we have unstable, both real and positive, we have unstable node. So we are going to have a moving away from the critical point. That's what this one has told us. That is at x equals 0, 0. What about the other one? Well, if you now say at um at 1 minus 1, okay, we have j of 1 comma minus 1, and that will be equal to, again, y is 1, so we have 1 minus 2 times minus 1, that's 2. So we have So we have 1, 2. Then down here is 2x. So 2x is 1. So 2 times 1 is 2. And down here we have 1. Okay. That's what we have. And so the eigenvalues can be found following this. So we just have 1 minus lambda, 2, then 2, 1 minus lambda. The determinant of this is equal to 0. So that means we have 1 minus lambda into 1 minus lambda minus 2 times 2, and that is equal to 0. So we have, so 1 times 1 is 1, 1 times minus lambda, that's minus lambda, another minus lambda plus lambda squared minus 4 is equal to 0. Okay, so that means that lambda squared minus 2 lambda, if we add these two together, then 1 minus 4 is minus 3 equals 0. So we need to factorize this, or we can use the so-called almighty formula. So here, the coefficient of lambda squared is 1, so A is equal to 1. The coefficient of lambda is 2, so B is equal to minus 2. And the constant is minus 3, so this is minus 3. So we can now find our lambda, we find lambda to be equal to minus B plus or minus square root of B squared minus 4AC, all right, all over 2A, so that lambda is equal to minus b is minus 2 here, so minus 2 plus or minus square root of minus 2 squared minus 4 into a is 1, and c is minus 3, all of this over 2 times 1. Okay, so lambda is equal to 2 plus or minus square root of 2 squared is 4 minus or minus is plus, 4 times 3 is 12, all over 2. And then we have lambda to be equal to 2 plus or minus square root of 16, all over 2. So that means that lambda is equal to 2 plus or minus 4, all over 2. So lambda 1 is equal to 2 plus 4, all over 2. And then lambda 2 is 2 minus 4, all over 2. Okay? So that means that lambda 1 is equal to 2 plus 4 is 6 over 2, that's 3. Then lambda 2 is 2 minus 4, that's minus 2 divided by 2, that's minus 1. So with this now, we have, this is a saddle because one is positive and the other is negative. So what do we say here? So we say at 1 comma minus 1, trajectories are drawn, towards 1 comma minus 1 along the stable direction, that is where we have lambda to be equal to minus 1. Okay, and away along, it is drawn away along the unstable direction, unstable direction. So the unstable direction is where lambda is equal to 3, like we got up there. All right. Characteristic of a saddle point. Okay. So we can say that this analysis illustrates how this phase plane analysis and the classification of equilibrium points provide a qualitative understanding of the system behavior. So we can understand the quality of a system by just doing this kind of analysis. But of course, Python is always there to also give us clearer picture. So imagine, so if you look at lines 8 and 9, we define the x dt to be x minus y squared, the y dt to be y plus x squared. So from there, so if you analyze this, if you run this code now, you can find, so see the trajectories now. So you see where you have 1 minus 1, it's a saddle. So you can see from one direction, you have the trajectories, moving away from that point, because it is a saddle. But look at this other one. It's a stable node. So you have everything. 0, 0, right? Is an unstable node. So everything is moving away from it. But for 1 minus 1, which is down here, so you see some points moving into it, whereas some points are moving outside of it. Okay. So you have a kind of saddle in that case. So that's what that is. Imagine, what if I change this second one to minus 2? Let's see what those things look like. Okay, so now you see the dimension changes. So this is unstable, and this one is also unstable in that case, because everything is just moving away from it. Okay, I mean some points are moving towards it, so it's still like a saddle. So that's how these things work. All right. So that's been a long one. Let's go back and just take some practice questions. You want to try your hands to see if you really understand all I've been saying all along. So let's talk about some practice questions. Okay. So, um, okay, should I do just one or two? Let me see. Let me see. Okay, I'll just give only one. So for the system for the system of equations, for the system of equations, the x, the t equals x squared minus y squared, and then the y dt equals 2x minus y. Okay, one, find the critical find the critical points of the system. Okay. Two, calculate calculate the Jacobian matrix. Calculate the Jacobian matrix at the critical points. Jacobian matrix at the critical points. Okay. Three, then you want to classify the equilibrium points. Classify the equilibrium points. Okay, say, is it a node? Is it a saddle? Is it a spiral? Is it a center? Want to check all of that out. And lastly, describe describe the qualitative behavior. Describe the qualitative behavior of trajectories. The qualitative behavior of trajectories near the equilibrium points. Near the equilibrium points. Okay. So those are the things we've done up there. So you want to try it on your own part also. Yeah, so let me call this A. So for the other ones, I'll just give the problems. I won't write all the. So you already know what to do. So the next thing is just do the same for B, where you have the x, the t equals x minus y squared, and the y dt equals x squared minus y. Okay, then let me say C now. The x dt is equal to minus x plus y. This should be really easy. And then the y dt, because the right hand sides are linear, minus y plus x. Okay. Let me find one more to add to this. Okay. Um, let me say D now. D, we have dx dt equals x squared minus y, and the y dt equals x minus y squared. All right, so let me see your answers in the comment section, either on Facebook or on YouTube. You can also find the code on Facebook, not on YouTube because I'm not able to put the code in the description box. So let me see your answers. Let me also see in the comment section how helpful those videos are for you. And if you want me to teach a topic or solve a problem, I may be able to find time along the line to do all of that. And then of course, be sure to subscribe to this channel. For those who have subscribed, thank you so much. For those who have not subscribed, you want to do that because you don't want to miss the other lectures coming. And I also want to hit the notification bell so you can always get alerted each time a new video is released. And don't forget to always like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye. Watch out for the next one. We'll be still talking about some of these things. Bye.